Welcome back. In this lecture, we continue with the discussion of Huntley's extension. That is, we would be using the extension of dimensional groups to reduce the number of non-dimensional pi numbers. Let's consider a simple example of a torsion of a shaft. A shaft is subjected to a torque T at this end. It is attached to a wall at this end. The twist phi of the shaft is a function of T, G, R, and L. We use the dimension M, L, and T. The T, time. We use the basic set of T, G, and R, and then we obtain a functional relationship that phi is a function of T divided by G R cubed and L by R. Then, as in the last lecture, we could use the information that twist should be directly proportional to the length of the shaft. More the length, more would be the twist, linearly proportional. So, the relationship between phi and L should be linear, and that's why the relationship should be phi should be L by R into a function of T divided by G R cubed. We know from our theory of mechanics of material that this function of T divided by G by R cubed is simply T by G R cubed, and so that the twist is L into T divided by G R raised to the power 4 times a constant. But can we improve the result from dimensional analysis alone? And we do it breaking them into the component length dimensions. Let's take dimensions in x, y, and z coordinates. Writing the dimension is not easy, so please pay attention. The force that is twisting the shaft, in fact, is a torque that is twisting the shaft. The torque arises because of force that we apply, and the force would have a dimension mlx t raised to power minus 2 or mly t raised to minus 2. In fact, the whole problem is symmetric in x and y. Z is a special dimension, but not x and y. X and y interchangeable. So, to preserve axial symmetry, we can take the dimension of force as m lx raised to power half, ly raised to power 1/2, and t raised to power minus 2. So, instead of lx or ly, we write lx raised to power half, ly raised to power half. This preserves the axial symmetry. Symmetry between lx and ly. Z is along the axis of the shaft. Similarly, the radius of the shaft, which is anywhere in x and y plane, and to preserve the axial symmetry, we write the dimension of R is lx raised to power 1/2, ly raised to power 1/2, and then the dimension of the torque would be force times the radius, and we can write it as m lx ly t raised to minus 2. And then the dimension of G, the shear modulus. Shear force per unit area divided by the angular strain. Force, as we see, is m Lx raised to power 1 half Ly raised to power 1 half T raised to minus 2. The area is Lx Ly. And the angular strain we write as R divided by length in the z direction. So the angular strain is written as this. If we were not using direction, this would simply be dimensionless. But it's actually in the R direction divided by in the Z direction. So it is written as Lx raised to power 1 half Ly raised to power 1 half divided by Lz. So this gives the dimension of G. The shear modulus is m Lx raised to minus 1 Ly raised to power minus 1 Lz T raised to minus 2. Notice that as in everything else earlier, Lx and Ly carry the same dimensions, denoting that the problem has symmetry between x and y directions. So this is the table of dimensions that we construct in M, Lx, Ly, Lz and T system. The dimension that we have calculated on the left has been transferred to this table. We use these 4 quantities as the basic set, and so we get only one pi number. Phi has a dimension of torque raised to power 1, G raised to power minus 1, R raised to power minus 4, L raised to power 1. And so we get phi G R raised to power 4 divided by T L as constant. Or the twist phi is function C T L by G R4. A very powerful result. Single constant can be obtained by twisting a single shaft and measuring its twist. We can obtain the value of C, and this will give you a relationship between twist and torque for any circular shaft of radius R, length L, and shear modulus G. Let's consider next an example from fluid mechanics. Let us consider a terminal velocity of a falling sphere in a viscous fluid. As a sphere falls in a column of viscous liquid, it accelerates initially under the combined influence of the weight and the buoyancy force. As it accelerates, the drag develops in the opposite direction, which increases with velocity. And when the velocity reaches such a value that the drag balances the net wet weight of the sphere, that is the weight of the sphere minus the buoyancy, then the sphere is said to have acquired a terminal velocity, a constant velocity which does not change. The terminal velocity has a great value in problems involving, say, a parachute. So this terminal velocity would be a function of the density of the solid sphere, the diameter d of the sphere, the density of the liquid rho f in which it is falling, the viscosity mu of the liquid, and of course the acceleration due to gravity. in terms of x and z and y coordinates. The velocity v has a dimension of z t raised to minus 1. The density rho s of the solid has the dimensions of mass per unit volume, and the volume is like x, y, z. So these are the dimensions of the solid. Same are the dimensions of the density of the fluid. The diameter of the sphere has xy symmetry. So we write this as x raised to power minus 1 half, x raised to power 1 half, and y raised to power 1 half. G is in the z direction, so it is z raised to power t minus 2. We have to worry about dimension of viscosity. How do we obtain the dimension of viscosity? We obtain with the relationship of the viscous forces from Newton's law of viscosity. The viscous force F is mu times area times the velocity gradient dv by dz. And so the dimension of mu would be the dimension of force in the z direction, mz t raised to minus 2, divided by the area, which would be yz, the side area of these, and the velocity gradient in that direction of the velocity field. So that would be z t raised to power minus 1 as velocity and d velocity by dx. So these are the dimensions that are obtained as m z minus 1 t. These are the two formulations, and from this we get this result. Out of these we can form two pi numbers. One pi number would be rho f by rho s, which is obvious since the dimension of f and s are same, and the other pi number is v mu divided by rho s g d cube. So that this pi number, which contains the dependent parameter